What's up guys, my name is Saurav and this is my YouTube channel Data Science Novice. So if you are new to this channel, please do like and subscribe. Your efforts are massively appreciated. So in the last two videos, we talked about what is GAN, how we train them, and what is the loss function. And in this video, we are going to see the implementation in PyTorch. So before we proceed in this video, I do expect from you that you have a prior experience in Python, PyTorch and deep learning model. And in this video, we are going to make use of MNIST dataset, which is already a very popular dataset in deep learning. And if you have been doing the deep learning, you must have come across this dataset. So I'm not going to explain what is MNIST dataset because you can Google search and you can find many articles regarding that. So let's jump to the Google Colab and do the coding. So here we are in the Google Colab and I have imported all the libraries that is required to build the GANs. So pause the video and type it out, or you can simply copy paste it from the GitHub link which is in the description box. So the first thing that we are going to do is to create a function that is going to visualize the images for us. And this is the same function that we are going to use during the training to check how the images are getting created by the generator. So we are going to name this function as show, and it is going to take 4 parameters. The first thing is image or tensor. The second one is going to be channel, since we are dealing with black and white images, so that's why it is going to be 1. The size of the images is 28 by 28. And the number of images that we want to show in one go, that is going to be 16, and you can change it later if you want to make it 20 or whatever number you want. Now we have to perform few transformation before we can visualize the images. So we are taking the input tensor and detaching it from its computational graph. That's why we are using detach function. Next we are moving it to the CPU because we do not want to use GPU for the visualization. And then the view function is going to reshape it into a tensor of shape 128, then the channel, and obviously the size of the image. So this reshaping operation ensures that the tensor has the desired shape. Okay, let's move on to the next line of code. Here we are going to create a grid of images using makeGrid function, and it takes few parameters. So the first one is going to be the data itself or the image. And here we are slicing the data using num variable. Next we have to pass the number of rows, which is going to be 4. So it is going to create a 4 by 4 grid. Next we are going to use permute function. So we are going to rearrange or reshape the dimension in order to make it more compatible with matplot library. Now we are going to call plt.imShow method and we are going to pass this grid. And finally, we are going to call our plt.show method in order to display the image. And that's it. That's all we have to do. And we have our function that is going to show us 16 images in a grid of 4 by 4. So next we will test our function. But before that, we need to initialize the training parameters and we need to download the dataset. So let's first start with parameter initialization. And why do we do this here? Because let's say we want to retrain the GANs by changing these parameters. So in that case, we do not have to look through the code. We just have to change it here and we can run the code without worrying about anything. So our first parameter is epochs. This variable is set to 500, representing the number of times the model will see the data set. Next we have current step initialized at 0. This variable will keep track of current step in the training process. Then we have info step set to 300. It signifies the interval at which we will print the information updates. Then we have mean gen loss and mean disk loss. These are initialized at 0 and will be used to calculate the mean generator loss and mean discriminator loss. Next we have our noise vector zdim, which is of value 64, and then we have learning rate. It is like a pace at which our model learns. So a small value often means more careful and stable learning. Next we are going to use our loss function and we are importing it from NN module BC with logistic loss, and it is suitable choice for our binary classification problem where we are distinguishing between the real and generated sample. Moving on to the BS, which is our batch size, it is going to be of 128. Next we have this CUDA. So basically the device. It is used for GPU acceleration. So if you are running this on a machine without GPU, switch it to CPU. So here we are ready with our training parameters. Next we have to download the dataset, and for this we are going to use MNIST function, and also we are going to use data loader function, which is a PyTorch utility function that help us efficiently load and iterate over the dataset during the training. So first we call our data loader function, and inside this we are going to pass MNIST function. Now this MNIST function is going to take few parameters. So the first one is going to be the directory in which we want to download the dataset. So I am going to download the dataset in present working directory. Next we have to set download equals to true. It ensures that the dataset is downloaded if not already present. Next we have to transform the data, and for this we are going to use transform.toTensors, which converts the images into PyTorch tensor, making them suitable for our neural networks. Then for the data loader parameters, we have to pass shuffle equals to true, because shuffling the dataset during the training is a very common practice which prevents model from learning the order of the example. Then we've passed the batch size, which is equals to PS, which is equals to 128. So let's run the code and see our dataset getting downloaded. So okay, oops, there is a typo error. Let me correct it. So here we can see that dataset is getting downloaded, and if you come to the file section, you can see the MNIST folder, and inside that we can see that our dataset. So one thing to note that these datasets are not downloaded permanently, and as soon as you end the session, the dataset will get removed. So we are done with downloading the dataset. Next we are going to build the generator. Now here first we will write a function that is going to work as a block. And in the generator class, we are just going to add these blocks to make our generator. Now why we are taking this approach? Because it will make our code less wordy, much more easy to understand, and making changes will be much more easy. So let's write this function, and we are going to name this function as gen block or generator block, and it is going to take two parameters, first for input dimension and the second one for output dimension. Now it returns something, and let's see what it returns. So we are setting up a sequential container, which is done by using sequential function of NN module. So first layer is going to be a linear layer, and we call NN.linear, and this transform our input to an output. So think of it as a key step in shaping our noise into something more meaningful. Next up we have batch normalization. So this helps us to keep our network stable and speed up training process, and it is applied to the output from the linear layer. And we finish off with a ReLU activation function for the non-linearity. The in place equals to true just means we are saving memory by modifying the inputs directly. So this function is pretty much straightforward, and if you have ever built a neural network before, you won't be having any tough time understanding it. And if you are facing any problem, I would recommend checking out my playlist on deep learning with TensorFlow. It covers various concepts and should help you clarify any confusion if you might have. Next we have our class called generator, that is going to be the heart of our GANs. So we are defining a class named generator that inherits from NN module, and this is the foundation for creating our neural network. So inside the generator class, we have an init method or our constructor, which initialize the parameters and layers of the generator. So we set the default values for three parameters. ZDIM, which is going to be our noise vector, which is 64. Then we have IDIM, which is input dimension or image dimension, which we set equals to 784. And last we have HDIM or hidden dimension, which we will use for creating the layers. Now next we have to call the constructor of the parent class, which is in this case is NN module. And this is basically a Python thing, and here I'm assuming you have a background in Python. So the explanation for this concept is out of the scope for this video. Next, we are initializing our generator network using nn.sequential function. This allows us to define a sequence of layers that will be executed in order. Next, inside the sequential method, we are just going to call our gen block function that we have already written. And in this function, we are going to pass our zdim or noise vector and input dimension, that is going to be our hdim as of now. So here you can see that how easy it is to create a layer by using gen block function, and it keeps our code clean. Now I just can copy paste these gen blocks and I will have a network. Now inside this function I just have to fill the numbers in order to create a neural network. So let's do this. So the first layer is always going to be an input layer. So we put our noise vector and then hdim, which is input and output respectively. Now for the second layer we have hdim, and let's say hdim multiplied by 2 as input and output respectively. Now why we have hdim? Because output of the previous layer will be the input to the next layer. And similarly for all these layers we have to do this. So let me quickly do this, and what you can do is to try different configuration at your end. Now the last layer need to produce our image. So for this we are going to use a linear layer, and the output for this is going to be equal to our image size, which we have already initiated in the constructor. So I'm going to use that attribute, which is idim or image dimension. Now to complete our generator, we append a sigmoid activation function. This is going to squash the values between 0 and 1, which is suitable for image generation. Finally, we define our forward function, and the work of this function is very simple. Take a noise vector and using generator generate an image out of that noise vector. And this forward function take only one parameter, that is noise. And in the return statement, we simply pass the input noise through the gen sequential module, because this gen sequential module contains all the layer that we have defined. And that's all what we have to do, and here we have our generator class. So if you have any doubt, please let me know in the comment section. I'm more than happy to help you. And if you are enjoying my video or learning from it, please do like and subscribe. Now on the similar lines, we are going to create our discriminator. So the first thing we are going to do is to create a disc block or discriminator block, and after that we will create our discriminator class just we did for the generator. So this disc block function takes two parameters, input and output. And in the return statement, we are setting up sequential container, just like we did in case of generator. So the first layer in our package is a linear layer. So this is a fundamental building block in neural network. It takes input and transform it to an output. And since we are dealing with the non-linear data, that is image data, we need to add non-linearity. And for this, we are going to use leaky ReLU activation function, and it takes 0.2 as a value. So this is the slope for negative input values. And this slide slope for negative values keep information flowing even when the input is less than 0. So here we are done with our disk block, and this compact blocks bring in non-linearity and complexity, helping our discriminator make more nuanced decisions. And now we are going to deep dive into the discriminator class, which is going to be similar but a bit different from the generator, because the work of the discriminator is to identify the images, whether it's fake or not. So here we are defining a class named discriminator that inherits from NN module. Now in the initialization method that is in it, we set up the architecture of our discriminator, and it takes two parameters, idim, which represent the input dimension or image dimension, and hdim, which represent the hidden dimension. And these parameters have a default value of 784 and 256 respectively. Next, we simply call the constructor of the parent class, which is in this case is NN module. Next, we are going to create our discriminator inside the init method. We define the layers of discriminator using nn.sequential container, because this allows us to stack the layer on one another. Now inside this, we are going to call our disk block function, and we just are going to stack these blocks in order to create a network. So let me quickly copy paste all these blocks. So let's fill the parameter for these functions. So the first layer is the input layer, which takes the image and transform it to in higher dimension of hdim multiplied by 4. And next layer takes the input from the previous layer and transform into some dimension, and so on and so forth. Now here you can create a different network than I have. You can simply increase the number of blocks, or you can decrease the number of blocks, whatever suit you, or you can change the number of neurons inside the layer. I highly recommend you to have a different network than I have, so that in the end of the video we have something to compare. Lastly, we create the output layer, and this is going to be a linear layer which simply has one neuron. So basically it takes the input from the previous layer and convert the whole information into a single value, that is whether the image is real or fake. And finally we define our forward function, and the work of this function is very simple. Take an image and using our discriminator tell us whether the image is real or fake. So in the return statement, we just have to simply pass the input image through the discriminator. So here we are ready with our generator and discriminator. Next, we are going to create a function that will generate the noise vector for us, because we need to pass these noise to the generator during the training process so that the noise get converted into image during the training process. So here we have our gen noise function, and it takes two parameter, number which represent the number of noise samples we want to generate, and zdim which represent the dimensionality of each noise sample. Inside the function we use torch.randn to generate the random noise sample. This function creates a tensor filled with random numbers from a normal distribution with a mean 0 and standard deviation 1. And finally we call to function and pass device to ensure that the noise tensor is moved to appropriate device. In this case we want it to move to GPU so that the computation is faster. Now since we have the class for generator and discriminator, we are going to instantiate the classes, or we are going to create the object for both the generator and discriminator. So first up we are initializing our generator with a specific latent dimension zdim or noise vector. Then we put it on the device. In this case it is a GPU. This generator is going to create the fake data, attempting to fool our discriminator into thinking it's real. And next we are setting up an optimizer for our generator, and here we are using Atom optimizer, a popular choice for training deep neural network. And inside this we pass the parameter of the generator, which are nothing but weights and biases, because that's what we want to optimize. And then we have learning rate, which we have already defined. Next we are going to do the same thing for the optimizer, so let's instantiate it. And then we are setting up the optimizer, and here we are going to use the same optimizer for optimizing the weights and biases. So now let's run this cell. Okay, so I'm getting an error because instead of using init I have written int, so let's correct this typo. So let's go back to the generator class, and here you can see that it is int. Let's correct it, and now let's go back to the code and let's run this cell again. And again here we are getting the error. This is because our computation is set to CPU and we have to change the runtime to GPU. So let's do this. So since we have changed the runtime from CPU to GPU, now we will have to run the cells again. So click on runtime and we have the option of run all. So click on that. So this will run the cells from the beginning. Okay, so here we are getting another error, and this time the error is coming from discriminator block. So let's see what's the problem. Okay, so we have made the same mistake of int and init, so let's correct it, and I hope this time I don't get any error. And here you can see that we are able to run this line of code without any error, which means that we have instantiated the generator and the discriminator block. So now let's call our generator and see the network architecture. And here we can see the network with all the parameters like input feature, output features, biases, and all that thing. Now the same thing can be done for the discriminator. We just have to call it. And here you can see the structure that we have built. Now next we are going to do a few things like taking a look at the data. Then we will try to generate random noise vector. using our gen noise function. Then we will use the generator on those random noise vectors. And finally, using the show function, we will plot those images. So first we are creating X and Y variables for images and labels respectively. Then we are making use of this function called next, which grabs the next batch of data, because as we know our data is in batches of 28. Then we have iter function, and this function converts the data loader object into an iterator. Next we simply print out the shape of the images and the shape of the labels, and let's print out the first 10 labels as well. Next we are going to create random noise vectors using our gen noise function, and as we know it takes two parameters. The first one is batch size, that is 128, and then zdim, which is 64. Next we are going to create fake images by passing these noises to the generator that we have built earlier. Then we are simply using show function and passing these fake images. So here we are getting an error, and this is name data loader is not defined. So let's check the data loader part. Okay, so this is not data loader actually, this is data. So let's change it. So here we see the X shape 128, that is because our batch size. And along with this, we have image dimension 1 by 28 by 28. And then we have Y shape, which is 28, which is again obvious. And we can also see the label for first 10 images. And finally, we have images in grid of 4 by 4. Since the network is not trained, and that's why we are seeing random noise. Next, we are going to calculate the losses for generator and discriminator, and these losses will get minimized during the training so that our generator and discriminator keep getting better with the training. So for this, we'll write another function, and this part is going to be a bit complicated, so make sure to understand it thoroughly. So let's first define a function for generator, and we are going to name it calculate gen loss. That takes in 4 arguments. The first one is going to be the loss function, which calculates the loss between predicted and target values. Then we have gen, that is generator model, disc for the discriminator model. Then we have number, and this is number of samples to generate. And finally zdim, that is a noise vector. Next we are generating random noise using the function that we have written earlier, that is gen noise. This noise will be the input to the generator, and this function takes 2 arguments. First one is number of samples we want to generate, then zdim, that is the size of each random noise vector. Now once we have the random noise generated, we want to create image out of it. So we are using the generator, and we are generating fake data by passing the noise through the generator. And this is where the magic happens. And since it is generated by the generator, we are calling it fake. Next thing is we need to test the images generated by the generator. And for this, we are passing the fake data through the discriminator to get its prediction. So this will tell us how well the discriminator can distinguish between the real and fake data. Next, we are creating target label for the generator. Since the goal of the generator is to fool the discriminator, we set these target labels to all ones, indicating that the fake data should be classified as a real. And for this, we are creating a vectors of 1 using torch 1 like. So this will create a vector of value 1 matching the prediction dimension. Finally, we calculate the generator loss using the specific loss function. This loss function compares the discriminator prediction, that is pred, with the target label, that is targets. And finally, we return the loss function for the generator. So if you are not clear about the function, I would say go through the video again. And if you have any doubt, let me know in the comment section. So now we are creating the loss function for the discriminator, and it is going to be more complicated than the previous one, especially if you haven't watched the theory video on how it gets trained. So I would suggest you to go through the previous video first and then come back to this section. So we are going to name this function as cal_disc_loss, that is calculate discriminator loss, and it takes several arguments. So the first one is going to be the loss function to compute the losses. Next we have gen, that is generator model. Then we have dist, which is a discriminator model. Then we have number, that is number of samples to generate. Then we pass the real data. And finally zdim, which is our noise vector or latent space. So first we are generating random noise using the function gen noise, and this noise will be used as an input for the generator to create the fake data. And again we pass two parameters here, the number of images to generate and the noise vector. Next we are just passing these random noise to the generator in order to create a fake data. So that's why we are calling it fake. Next, we simply pass the fake data generated by the generator through the discriminator, and here we have to use detach function, and it is used to prevent the gradient from flowing back to the generator during this step. And why we want this? Because we typically want to update the discriminator parameters based on the real and fake data while keeping the generator parameters fixed. Next, we simply create a target label for the fake data. Since the discriminator aims to distinguish between real and fake data, the target label is going to be fake, or we are going to set it equals to 0. So we are making sure that discriminator knows that this is a fake data. Next, we simply create the loss function for the discriminator on the fake data. So we call the loss function and then we pass the prediction made by the discriminator and the actual labels that we set. So basically in this part of the code, we are trying to help the discriminator to learn that this is a fake data and you need to understand it better or need to classify it better. Now similar thing we have to do for the real images, because as of now discriminator can only understand the fake data part. Now we have to include the real data part. So we pass the real data to the discriminator directly. Then we are going to set the target label for real data as 1, because these are real images and we want the discriminator to learn this thing. And for this we are simply creating a vector of 1, which basically is representation of real images. Moving on to the next part, here the loss for the discriminator on real data is computed using the loss function. And here we pass the prediction made by the discriminator and the ones we set. Now, in order to get the total discriminator loss, we simply take the average of fake image loss and the real image loss. And this is a widespread practice in training the GANs. Finally, we return the discriminator loss computed in this function. And with this, we have completed yet another complicated part of the GANs. Now, we have everything at our hand to train the GANs. Next, we are going to make use of everything that we have built and train the GANs, which is going to be the most exciting part about this whole video. So let's do that. So first we are going to use the for loop, and since we have set our epoch equals to 500, this loop will run for 500 times, or in another way we can say that the model will see the data for 500 times. Next, inside this loop, we are going to have another loop on the data loader iterator, which has our data in batches. And it outputs two things, that is images and the labels. And since we do not use label corresponding to the image, we simply store it in underscore, which means it's not important. The only part that is important is the data, which is stored in real variable. And here we have used tqdm library in order to see the progress bar of the training. Next, we reset the gradients of discriminators parameters to 0 using the 0grad function. Now this step is crucial as it ensures that the gradients of all parameters being optimized by the optimizer are set to 0 before performing the backward pass. By resetting the gradients, we prevent the accumulation of gradients from the previous iteration, allowing us to compute gradients solely based on the current batch of the data. Next, we simply store the length of current batch in this variable, and then we have to reshape the real images to have a flat representation. And for this, we are going to use view function, and the -1 is going to flatten the images. And we are doing this to match the input size expected by the discriminator. And then we move this data to a specified device. In this case, we are going to use GPU because it is going to train much faster than the CPU. In the next step, we are just calling the discriminator loss function in order to calculate the loss. And then we are simply passing all the parameters like loss function, generator model, discriminator model, current batch size, real images, and ZDIM or size of the noise vector. In the next step, we are just going to use backpropagation. Alternatively, we are computing the gradients of the loss with respect to all the parameters of the discriminator network. And for this, we are simply using backward function, and then we set the retain graph equals to true. It's an optional argument that specifies whether to retain the computation graph after the backward pass. So this typically is used in scenario where multiple backward passes are needed within the same iteration, such as in the case of training GANs. Next, we are going to repeat the same steps for the generator part. So let me fast forward this video, or you can simply do is copy paste the same code and make the changes here and there. Now, one thing that I forgot to do is updating the parameters of the discriminator network based on the computed gradients. So for this, we use step function of the optimizer. So we have to call the step method of discriminator optimizer as well. Basically, this step method performs a single optimization step adjusting the parameters of the network based on the computed gradients and the optimization algorithm used. Next, we are going to accumulate the losses for the visualization purpose, and this is we are going to do for both the discriminator and the generator. So mean discriminator loss, and then we call our discriminator loss, and by using item function or method we are extracting the scalar value because that's the only thing we need, and then we are simply dividing it by info step. And let's do the same thing for the generator loss. Now here is the thing, either I can train the GANs and then check the images created by the generative model, or I can simply check how the model is doing at certain intervals. So for this, we are going to make use of current step, and in this case, after each 300 step, we are going to see the images generated by the updated model and all the informations. So if the current step is divisible by info step, which is 300, and the current step is greater than 0, we are going to create a fake noise data by using our gen noise function. And in the next step, we are simply calling the generator model which is updated and passing the noise through it. Then in the next step, we use our show method to see the fake images generated by the model, and let's also print out the real images. Then in the next step, we are printing the following information using the f string literal, that is epochs, then the current step, then mean generator loss, and finally mean discriminator loss. And finally, we set the mean generator loss and mean discriminator loss equals to 0 so that we can start fresh for next current step. So in summary, this block of code is responsible for periodically displaying or logging information during the training. And finally, after all this, we simply increment the current step by 1, and that's the breakdown of this GAN training loop. It iterates through epochs, processes batches of real data, updates the discriminator and generator parameters accordingly, and provide visualization and statistics for monitoring the training process. And now let's run the code, and I hope I don't get any error this time. And here we can see that the training has started, and here we see the training progress bar. Then we can also see some informations that we have printed out. So now I'm going to fast forward in time and show you when there has been some training and our generator model is able to produce some images which look a bit like actual images. And now here we see that our generator model is starting to create fake images for us, and you can leave this training to happen for a little longer and check after some time that how is image getting created. So in the next video, I'll show you how you can save the model at specific interval of time and how we can use a website to check the training progress or all the losses and everything. So as of now, I end this tutorial here and I hope you have enjoyed building your first GAN. So see you in the next video. Till then, bye, stay safe and don't forget to subscribe.